We've previously talked about heart rate and stroke volume, and we put those together and we get cardiac output. And so this video is going to focus on cardiac output. And we've got these four outcomes that we're going to go through. Okay, so cardiac output, often it's abbreviated as Q subscript C or CO. Q is often referred to as flow or used for flow. The reason we use QC as opposed to CO is oftentimes people confuse or think of CO as carbon monoxide. Ultimately, cardiac output is just how much blood is pumped out of the ventricle in a single minute. So if we're going to calculate it, it's pretty simple. It's heart rate times stroke volume. And so there's going to be some math in this video. Okay. When it comes to cardiac output, we express this as liters of blood. And that's a big deal because stroke volume we express in milliliters of blood. And so you're going to have to remember to divide by 1,000 when you calculate cardiac output. Okay, so let's just go through an easy example here. So let's say your end diastolic volume is 160, your end systolic volume is 60. Well, that would mean your stroke volume is 100. 160 minus 60 is 100. So if your heart rate is 70 beats per minute, what's your cardiac output? Well, in this case, you'd take 70 times 100. That equals 7,000 milliliters per minute. But we divide by 1,000 because we want it in liters. So that's 7 liters per minute. So how does heart rate and stroke volume affect cardiac output? Okay, again, here's our equation. And so if heart rate goes up, we're going to increase cardiac output. Now there's an assumption that we're making here. If heart rate goes up and stroke volume remains constant, then cardiac output will go up. The same is true of stroke volume. If stroke volume goes up, we're going to assume heart rate remains constant, then cardiac output will go up. Okay. Usually, or what often happens, is one variable will increase when the other decreases to maintain cardiac output. Okay? Ultimately, we're trying to maintain that flow. So this leads us to cardiac reserve. And so it's just the difference between your current cardiac output and your maximal cardiac output. Okay? So we can use this to get an idea of how healthy, cardiovascularly speaking, someone is. High cardiac reserve is good. Low cardiac reserve is bad. Okay, so let's just assume that typical resting cardiac output for an adult is about 5 liters a minute. We'll just say that. Let's just say you're an elite athlete, okay, where your maximum cardiac output is 40 liters a minute. And there's very few people in this world where that would actually exist or be true. But in that case, you would say that reserve cardiac output is 40 minus 5. That would equal 35. Okay, that's really good. But if you're at rest and your resting cardiac output's really close to your maximal cardiac output, that's not good. Then we've got ejection fraction. So ejection fraction is just what percentage of your end diastolic volume leaves your heart during a contraction. So again, some more math here. So it's stroke volume divided by your end diastolic volume. Okay, typically it's about 50%. Your heart never ejects all of its blood. That's a good thing. I haven't actually ever checked this out, but I've been told that if your heart is completely empty and it contracts on itself and the walls hit each other, your heart just stops working because there's no sense to work if there's no blood in there. Okay, this is a percentage, so remember to multiply by 100. So here we've got an example. In this case, end diastolic volume is 140, stroke volume is 70, end systolic volume is 70. Okay, that means your stroke volume is 70 milliliters. So you go 70 milliliters divided by 140 milliliters, and that would mean your ejection fraction is 50%. So we ultimately use this to determine heart function. This is actually something that they do measure or have been known to measure during the NFL Combine. Several years ago, a defensive lineman from the University of Utah, a guy named Star Latulele, I don't remember how to say his name exactly right. I believe he played for the Ravens for a number of years. He was set to be a number 1 top draft pick. They measured his ejection fraction. It was like 30%. And he went from being like a first-round draft pick to like a second or third-round draft pick. Cost him millions of dollars. The good thing was they were able to find the problem, correct it, and he went on to have a really successful career, which pains me to say as a BYU alum, but that's all right. Okay, so normal function, 55 to 70%. If you've got less than 40%, like Star did, that's bad. Okay, so usually we say that someone has heart failure. So at the end of this video, can you do these 4 things? Can you describe the relationship between heart rate, stroke volume, and cardiac output? So basically give me the equation. Can you calculate the cardiac output? So for example, if heart rate is 50, stroke volume is 80, what's your cardiac output? You can email me if you think you want if you want me to check your answer. Define cardiac reserve and define and calculate ejection fraction.